It's always a highlight of my year to come for a longer visit here to the ICTS, and I want to explain, was asked to explain sort of some introductory talk about sort of generalized hydrodynamics, but the emphasis will be on classical integrable systems. And so I want to start off with sort of just sort of, really very introductory chapter, which sort of gives sort of the idea what I mean by the hydrodynamics. Okay, so this is sort of the first thing. So this is sort of the ballistic, or if you want, so the Euler scale. And let me start just from a microscopic conservation law. So, the underlying dynamics is pretty general, or it could be quantum, or maybe stochastic, anyway. I mean, so you have sort of some field. So this is a P. I mean, this is supposed to be a capital rho. I mean, so you have the field rho at x of t, and you look at its time evolution. And it so happens that it satisfies a conservation law, which means that there's another field which is called J, and it's also a function of maybe before saying this, actually, I mean, we're looking here at integrable system. So this means that basically I'm reduced to 1 + 1 dimensions. I mean, one space and one time dimension. I mean, this, of course, there's a lot of ideas of extending this somewhat further, but I'm just looking at the standard case. So I will have, I mean, the xt will be okay. So it's 1 + 1 dimension. This is what I want to say, and eventually, I mean, the size of the system and time will be, of course, very large. I mean, so we have many degrees of freedom. And so it's not the usual integrable systems where you have only a few degrees of freedom. Anyway, so I wanted to write down this conservation law. And now the point is that you want to sort of understand somehow the dynamics for very special initial conditions. I mean, not, for general initial conditions, presumably there's very little you can say. But I mean, you want to sort of, let's say I have here the P, and maybe I look at first at time t equals 0, and I basically sort of impose some initial condition, which, what this picture should indicate is that it has sort of a slow variation on the microscale. And so typically you will see this, but I mean, you will see also sort of small fluctuations around this picture. Okay. And then you sort of, evolve your underlying dynamics. I mean, so now there will be sort of like a t-axis. And what hydrodynamics sort of wants to do is it wants to sort of somehow predict what is the dynamics governed on the macro scale. I mean, which means that, I want to figure out what is the equation for the evolution of, the typical profile. And to do this, so now I want to do the macro scale. And the idea is that when I look at a sort of rather small volume element over here, so maybe I look at this volume element, I can sort of essentially think of this envelope to have a constant value. And, the dynamics assumed to have maybe only this one single conservation law. And it has sort of the property that, when you look in a small cell, it actually wants to sort of reach a steady state. So here you will have a steady state. And this will be just, if I only have a single conservation law, will be characterized by a density, which of course it's a density at the point x, and then as it evolves at x and t. And so you write down the macro equation, so that's ddt. Now we have a deterministic quantity. I mean, these objects are typically sort of, you should have think of them as random because, the underlying dynamics has some sort of randomness in it. But now we have a deterministic equation. And now the great idea of hydrodynamics is that, I mean, this is sort of, nothing very deep. I mean, I'm just using the law of large numbers. in order to sort of, describe this curve. But then the big thing is that you want to, you have to also figure out, what is this current? And here, the idea is that what you do is that you do a local computation. So here you have maybe a given density. So this is your rho. And for this density, you have a steady state, which depends on rho. And in this steady state, which is a random state, you actually compute what is the average current. Okay, so there's a density current relation, which sort of is computed from the steady state. And if this such a kind of thing exists, then of course your macroscopic equation is equal to 0 is simply this one. Okay, so this is this is sort of the evolution of the macroscopic equation for the solution for the macroscopic profile. Okay? So it's a very simple idea, but it's very powerful. Of course, the idea to have only a single one is sort of a little bit well. There are systems which only have a single conserved field, but it's a little bit limited, and so maybe you want to have several conservations law. Maybe there's a kappa and which labels the conservation law and goes on. But then it's rather easy to generalize this equation. Now you will have a density which depends. Well, I put here kappa. Okay, so let's keep kappa as an index. Well, then of course the current will depend on kappa. And now, of course, this current will be a more complicated function because it will depend on all the fields. So, I have to put here a little vector sign so that, I remember that's now really a functional, of possibly of a large number of these densities. Okay? And the idea of generalized hydrodynamics is that actually you're looking at system, where on these large scales, you have an infinite number of conservation laws. But, for each one, you still have sort of, this idea. Of course, now it's more complicated because, J will be a rather complicated functional, and it's not so easy to figure out what you have to do. But in principle, what you have to do is, you have sort of, that's a program for this lecture. You have to first figure out what are the steady states. Okay, and then for the steady states, you have to sort of say something about you have to say something about the densities. Okay, and sort of typically, the most difficult thing is actually to look at the average current. So let me put here just the currents. Okay. And so this kind of program, I want to sort of explain to you in the context of classical integrable systems. And let me see, I wanted to say one thing. Yeah, okay. So, okay, so now there's sort of one remark which I sort of want to do. The way how I wrote it is that nature is sort of arbitrary, and then maybe you can have systems with 17 conservation law, but that's not the case. There's sort of like a dichotomy. You can have either few or you can have infinitely many. And this is sort of actually, it's not really known in sort of great generality, but there's a very beautiful work by Cergy, who actually looked at this issue for quantum spin chains in one dimension. And he assumes to have a Hamiltonian which has next nearest neighbors, but otherwise completely arbitrary sort of coupling coefficients. Okay? And so what he proves is that you have either have a trivial number of conservation law. This is typically, you could have, one which is only the energy, but there could be spin, and so maybe it's 1, 2, 3, 4. It depends a little bit on the model. But anyway, trivial, the ones which you see are obviously, when you look at the symmetries of the model and you sort of figure out immediately what the conservation laws are. So you have either trivial or you have infinity. There's nothing in between. And so in some sense, what this means, we can do either in the trivial case, when we know that there are only a few conservation laws, then we can do conventional hydrodynamics, which of course has been around for a long time, or we have the case of infinite number, and that's the generalized hydrodynamics. Now, I think, you know, these techniques are a little bit special for looking at quantum mechanical systems, or in particular spin systems. And anyway, you know, presumably it's in some sense also true for other systems. But anyway, I mean, in this case, we have a very nice result. Okay, yeah, okay. And then now I wanted to say a few words about, maybe I can put this down here. You know, sort of there is, I'm doing here, you know, okay, okay, so here I can put it here. So, you know, there's a classical, now of course, you know, in this audience, there are many people who work on GHD, and it's mostly quantum, right? I mean, so there's sort of this sort of issue that, you know, I first have to do sort of make a decision, and then, you know, by title, I mean, you know, I want to look at classical models. I want to think of them, you know, as standing on their own foot. I mean, so, you know, there's no help from quantum mechanics at all. I just have to look at the classical model and see what I can do. But I want to point out that, you know, that there is sort of a slightly, you know, sort of more sophisticated relation. I mean, you know, I mean, Alvise is sort of one of the top experts in this area. What people have done is that you look at quantum systems and you take the semi-classical limit, and then you might get sort of interesting information about the classical GHD. Okay, so I'm not touching this point. I just say that this, you know, if it works, it's a very powerful sort of method, and it does work in several models, but it's sort of, you know, besides what I want to tell you here. So here at that moment, I mean, you know, I cross out the quantum, and you know, I'm just talking about classical systems. Okay, so the next issue, I mean, what kind of classical systems are we looking at?
Sorry, can I ask one question? So this Shiraishi's proof, how did it sort of go? I mean, the trivial or infinity? Is it some complicated?
Yeah, to all orders, yeah, okay. No, it's a, well, I mean, he's whatever, mathematical physicist, but it's a proof, I mean. Well, you know, it's a complicated linear system. You have to look at the number of zeros somehow. I mean, anyway, I cannot go into this here now, yeah, but it's, no, I mean, you know, and it's ongoing, it's sort of ongoing work, right? I mean, you know, the first results were for nearest neighbors and next nearest neighbors. They extend these things to higher dimensions and all kinds of things, right? I mean, but it's I think it's very nice work. Thanks.
Does the dynamic have macroscopic number of conserved quantities, or exactly the same number?
Well, I mean, what I mean by infinity, of course, depends on the model, right? I mean, so, you know, I mean, how you know, how I do the labeling of this infinite conservation laws, I mean, that's sort of, you know, for each model sort of different, right? You see, I mean, okay, I mean, this is one thing. You know, when I saw steady states, you see, this is sort of one thing you have to figure out, or densities, you have to figure out, you know, how many conserved fields you have. I mean, that's sort of one basic step. And if you don't understand this, I mean, there's no chance to write down the correct hydrodynamic equation. Okay, so let's see. So what? Yeah. Now the question: what kind of systems do we look at? Of course, I'm not you know, in this lecture we'll cover not everything, but I mean, just to give you sort of a slightly broader feeling. So first of all, there's sort of nonlinear wave equations. And well, I just give you know, the letters. I mean, so it's the Korteweg-de Vries equation, which is sort of somehow the most famous equation in this area. But then you know, you have something like the nonlinear Schrödinger equation. Maybe you have something like Sinch or Sine-Gordon equations. Now, these nonlinear wave equations, they could be also sort of discretized. I mean, you have a discretized version of the NLS. I mean, so this is the Arvelig-Sladek equation. Then you can discretize even more. You get the box 4. Anyway, and then the list goes on. I mean, so I'm just telling you a few of these models which have been, there's huge subject, and many people have worked on this. I mean, and the list is sort of only partial. Okay, then you know, then there's sort of a second class of things which I sort of call more particle-based. So here you have, like, I mean, what I'm going to tell in detail. I mean, the total lattice. I mean, you have the Calogero models. Then you look in the literature. I mean, there are many more models, but you know, when you sort of insist that these models should have some sort of, you know, you can write down mathematical models, but you know, they should have some sort of connection to physics. I mean, then you know, the list is not terribly long. I mean, of course, you have the hard ones here also, now the list is actually not really disjoint. I mean, you know, this I'm going to explain. I mean, maybe the Toda appears also here, and the Abel-Ladek might be appearing over here. So you should not think of it sort of as a totally disjoint list, but still, you know, somehow the way you treat these systems and these systems sort of go in slightly different directions. Anyway, so this is sort of typically the universe of integrable systems which people work on. Okay, and yeah, okay. So now I want to come to the second point, which is the Lax matrix. And you see, I mean, everybody, you know, at least sort of in most cases in your whatever, your basic class of mechanics, I mean, you learn about integrable systems. And, you know, you have sort of this nice picture. I mean, you have the action variables, and the action variables sort of define some sort of parameter space. And then you have the angle variables, and so your phase space foliates into tori. And then on each tori, I mean, you have this quasi-periodic motion. I mean, this sort of at some stage of your life as a physicist, you presumably have learned this. This picture is, of course, also true for if I take, you know, a huge number of degrees of freedom. But, you know, toris in a large dimension, I mean, what are they? And if you want to do generalized hydrodynamics, this is totally useless. I mean, you never use this kind of sort of intuition, right? Of course, it's correct, and for small systems, you know, for small numbers of degrees of freedom, it's extremely valuable. But once I come here to the hydrodynamics, simply forget about it. Okay. However, the main technical tool is the Lax matrix, and so I want to sort of explain this a little bit before I come to the concrete system. So Lax, Peter Lax, I mean, he is a, you know, extremely famous mathematician. I mean, you know, PDEs, I mean, partial differential equations. He built up the computing center of the Courant Institute, which was sort of, you know, a model for many computer centers worldwide. I mean, I remember when I was in New York, I mean, the only place where you could do sort of serious computations was the Courant Institute. I mean, you know, he has many prizes, and so, you know, he's really extremely famous. I mean, he died this year at the age of 99. So the famous work of Lax, which I'm referring to, is now from 1968. So it's a pretty long time. Okay, and so what he looked at was the KdV equation. So this is one of these nonlinear, and I write it as ddt. So of course, I mean, U is the wave field. But you know, it's 1 plus 1. It's just in one dimension, and then it's written. I mean, I like to write it as a conservation law, and it happens to be 3u squared plus dx squared times u equal to 0, right? Okay, so this is the equation, and now people, of course, suspected that this is an integrable equation, for instance, in the sense that it has many conservation laws. But sort of the main tool was to observe that there's a Lax matrix. So the Lax matrix, so in this case, because we're working on the continuum, it's actually an operator in infinite dimension, but later on for the Toda, it will be just sort of a large matrix. So people call it always Lax matrix. And in this particular case, it's sort of a very familiar object. It's really essentially the Schrödinger equation in imaginary time. So here you have minus the x squared, and then the potential is the u, and of course, you know, it's a solution of this equation. So I put a t of x. Okay. So I hope everybody sort of understands my notation. I mean, so you know, it's just think of a Schrödinger equation. I mean, then you have here the kinetic energy, and this is a potential, but this potential is now depending on x and time. And of course, through this, I mean, you get the connection to the KdV equation, right? Okay, so what? I mean, yeah, of course I can write this down, but now the point is that this matrix has a very important property, namely, so you should think of this as an operator depending on t, right? And so I can take the derivative, and then what you find is that you can write this derivative in terms, I just want to get the order right, in terms of another operator like this. This is sort of called the Lex pair. And this is sort of the crucial identity, which sort of, of course, it's a highly non-trivial property, but the models which we study in the classical scheme always have a Lex matrix. If you don't have a Lex matrix, just forget about it. See, basically, it's the only tool which we have. It's similar, like, you should compare this to quantum system where, one of the basic things is to have a beta ansatz. Right? I mean, if you don't have a beta ansatz, I mean, you're in trouble, right? And here it's sort of, it's not a formal analog, but sort of in terms of importance, it's the same thing. Okay, so now why is this important? Well, because you see what this tells you that L of t is isospectral. So you see, I mean, this operator, as you well know, I mean, can have both continuous spectrum, we can have eigenvalues, but the assertion is that it just comes directly from this commutator. The assertion is that when I look at it's a symmetric matrix. I mean, so I have real eigenvalues. The assertion is that when I look at this matrix, let's say at time t equals 0, it has a particular spectrum, but then when I look at the same matrix at time t, it will have still the same spectrum. This is what I mean by isospectral. All right, so now let's take the next example, which is sort of closer to what I want to explain. So let's look at the total lattice. And okay, so now you have positions, and now you have n particles. And okay, so let's see. So yeah, so e to the minus rj minus e to the minus rj plus 1, and this is of the potential difference. I mean, so the rj is the qj plus 1 minus qj. So these are the sort of whatever Newton's equation for the total lattice. So this is the second derivative here. And this it lives on R. I mean, the positions are sort of at the moment on R. Maybe there could be boundary conditions, which maybe I'm going to discuss. I mean, plus boundary conditions, but let's just look at this for just a moment. I mean, so what you have is sort of the real line, and here you have these particles, and then they are moved. So the particles are labeled because they have I mean it's not permutation invariant under labeling. I mean you know what I mean you have to look at a specific pair here, but not ordered. Right? I mean this could be particle 1, and then maybe here I have particle 2, and then here I have particle 3. Okay, so, but I wanted to say about the Lex matrix. So in this case, the Lex matrix is extremely simple. It's a Jacobi matrix. So it's a triangle matrix. So out here you have zeros and zeros. And maybe depending on the boundary condition, maybe I should put a little dot for the experts. I mean, there could be, through the boundary condition, you could have some matrix elements over here, but that's not so important. But the main point is that when I look at the diagonal, I mean, then, I just put all the PJs. Okay, and then on the off diagonal, I put the HJs is up to an minus 1, and here I do the same thing. Okay. So it's a symmetric, it's a triangle matrix, and what I have not defined for you are the A's. So the HJ, of course, depend on the R's, and okay, so maybe I should mention the name. So these are the famous Flaschka variables. So now we are 1974. I mean, Flaschka was also at the Courant Institute. And of course, I mean, you know, he was in this environment where he was, you know, sort of looking at these kind of properties. I mean, Toda was doing something else, but I mean, Flaschka, of course, knew that he had to find the Lax matrix, and he did. And so he defined the HJs to be equal to e to the minus rj over 2. And then you have, again, the same identity. I mean, so I evolve all these objects according to this equation. And lo and behold, as if I take the time derivative of this matrix, then you know, it will set there will be this commutator. And in this case, I mean, here I didn't tell you what the you know, the pair, the second member of the pair is, but here the B is sort of, fortunately, quite simple. So it's 1/2, and then on the diagonal you put 0, and here you put minus HJ. Okay, here it's 0, 0, and 0, and here you put the plus HJ. Okay, so you see that the Lax matrix is symmetric. This is anti-symmetric. So this will generate a unitary group, and here we don't really look at the dynamics usually. I mean, okay. All right. Okay. So then there is sort of well, okay. So maybe I just put this as a remark. I mean, you have to sort of look a little bit at the boundary condition. I mean, there are typically two boundary conditions. What you want to do. There's one which is usually called open. Open basically means that I take n particle and there's no confinement. So they can sort of go anywhere where you want. And closed, I mean, typically you put something like periodic boundary conditions in the right way, but these are it's just the terminology. Okay, so now I want to come to what I call the Lax microscope number 1. There will be a second one. That's the first use of the Lax microscope, and it's the following question. So I give you some configuration, right? I mean, so you know, some I don't know, 1,000 particles, and you know, I give you the positions and the momenta. All right. Okay. So here. Okay. So I'm just doing this symbolically. I mean, so here I have this many particles. And now I ask the question, let's take a little subsystem. I mean, maybe this one. Discontinuous, right? I mean, so, and then you ask yourself, maybe wait a second. Okay, so you know, it's fine. So okay, so no, maybe I should make this remark. I mean, so you see, I said LT is isospectral, right? So this LT, of course, is also isospectral. So you know, here now we have a discrete eigen. You know, we have just n eigenvalues. And isospectral just means that these n eigenvalues do not change. So, you know, just looking at the eigenvalues, I know already what the conserved quantities are. Okay, maybe eigenvalues aren't, you know, maybe you have to take combinations, but you know, you get, if in a very trivial step, I mean, you observe the fact that you know you will have n conserved functions in for that mechanical system, right? And it just comes directly from. Just follows directly from this commutator relation. Okay, so
sorry. So the spectrum is supposed to be here.
Yeah.
The spectrum is supposed to be non-degenerate.
What?
The spectrum is non-degenerate. I mean, the eigen.
Okay, that's a good question. I mean, for the Toda, one actually knows that for every configuration, the spectrum is non-degenerate. Okay, for other systems, I mean, it's often sort of you know, a probability 1 statement. I mean, at the moment, I haven't talked about randomness at all, right? I mean, I'm just looking at the given configuration. For the Toda, I know that it's non-degenerate.
How about for the KTV?
I wouldn't know. No, I think not. I mean, well, no. I cannot believe. I mean, you see, I mean, if I put here U, I mean, of course I can put a U where you know, 2 eigenvalues are sitting on top of each other, right?
So isospectral in that case would mean that the degeneracies as well as the
no. I think when I talk about isospectral, it's really in terms of usual spectral theory. I mean, you have to you know, it's the value, and then I have to also give the degeneracy both for the discrete and for the continuous spectrum. Yeah.
Thank you.
Yeah. Okay, so let's see. So what? So now okay. So I'm coming back to this question, and so now you know, I ask you, what is the value of the conserved quantities for that particular configuration? This would be even an experimental question. You want to know what is the energy, what is the momentum, same thing. Okay. So now there's actually an experimentally used method, which is the time of flight. And what you do is, so here you have my initial configuration. So first you isolate everything, right? You sort of throw away what is outside. So here I have sort of my small subsystem, and then and then you simply decide to look at very long times. So they are close and they interact in some way which you don't know, but you can just wait. And if you wait long enough, what you will see is that you will see sort of trajectories going this way. This way, and then maybe this way. And this follows very easily when you look at the Lax matrix. You see, it's e to the RJ. It's a repulsive potential, and so in the long time limit, these A's will just go to 0. And so at very long times, the Lax matrix will be diagonal, but it's isospectral, and it's already a diagonal now. So what I have on the diagonal are really the eigenvalues. And so you see that when I sort of sample these velocities, I have solved my problem. This is how they do it experimentally. At least, maybe not for the TODA, but for other systems, but it's certainly one way to do it. But now the Lax microscope says, look, I can be much more clever. All what I do is, I take L for that particular configuration. So then I ask my program to solve the eigenvalue equation. So it will spit out the eigenvalues, and then I know the values of the conserved quantities. So this is what I mean by microscope. It's sort of course, it's a somewhat non-trivial machine because I have a matrix and I have to find the eigenvalues. But it's a very clear mathematical prescription, and if you have a computer, you can easily do that. Okay. The reason why I wanted to emphasize is that later on we will see a Lax microscope too, which is sort of much more sophisticated. But there's some question.
Can these tau j go to minus infinity? Can these variables go to minus infinity so that AJ will become plus infinity?
The Qs or yeah, sure. Well, I was a little bit sloppy. Here, for this particular case, I'm sort of assuming that everything is on the real line, so they can go to minus infinity. Yeah.
But then you will not be able to say that it is.
Well, no.
You said AJ has to become.
No, they separate. This is the difference, right? And so in the long time limit, the RJs will go to plus infinity, right? Because the particles are repulsive and they sort of go further and further apart, and so the A's, this term will eventually be 0.
Not if tau minus infinity, no?
No, you see, I'm in the situation. Of course, you see, if I would confine the system, then of course I cannot make this argument, right? But here I'm looking at the infinite line, and then so I'm looking at the scattering situation where there's no confinement, right?
Okay.
All right. Okay, so let me see. Okay, so now, yeah. Okay, so this was the thing, and now the next chapter is comes sort of okay. So but what I'm going to do now is sort of going somehow a little bit through this program here, right? So we have already done one. We have already because I have the Lax matrix. So I continue with TODA. We have the one step, we have the Lax matrix, we have the eigenvalues, they are conserved. So we have found, the conserved quantities. And now the next thing what we want to do is, we want to do hydrodynamics. And maybe I didn't emphasize this so much at the beginning, but, hydrodynamics is always assuming that I sort of prepare not just one given initial condition, but sort of I have a random initial conditions, right? So this is sort of, and so chapter 3 is random, what did I call this? Stationary states. You see, I don't want to, states. You see, I don't want to put equilibrium because I mean these are not the usual equilibrium states, right? But of course, you know, they have the same property that these are statistical states which are not changing in time. And you know, here of course it's usually called generalized Gibbs ensemble in the context of the TODA and so okay, so I mean this is stat mac, right? I mean you're just doing stat mac now. Okay, so let's see how we do this. Okay, so first, I mean, you know, I fix n. Maybe n eventually will be large, but I fix n. And okay, so now you see, I mean, we have somehow, you know, the Flaschka variables is not in the P and Q, but sort of it's really in the R's and well, no, it's really in the A's. I mean, okay, so maybe writing down, you know, this Gibbs measure, it's sort of natural to actually use the A's rather than the P and the Q's. And so this is what I'm going to do. Okay, so n is fixed at the moment, and then I write down the distribution directly, 1 up to n. Okay, so now I have to. Okay, so now I have to put the HAs. Well, you see, if I take really 0 here, then you know I have 1 less. But let's not worry too much about this. So you know, if I compute the Jacobian, I will get this object down here. And now the question is. I still, you see, I want to write down the a priori measure, but you know, usually you should still put the density there, right? I mean, so I want to multiply this. It's still all product, right? I want to multiply this with e to the power p. So p is not the row from before, but let's have a look at the second. I mean, what this is here. So this is e to the minus p. Rj minus Rj plus 1 minus Rj over 2, right? I mean, that was the definition. I mean, where was here? It's sitting over here. And so you see that I mean, first of all, you know, this is the density. If I do the sum over the thing, it's telescoping sum. So here I will see something which is invariant under time. And you see, it's sort of the you know, sort of the control parameter. Sorry, this is a wrong definition, but I'm putting here. No, it's just the Rj. Sorry, I was just sort of mixing this up. Okay, so it's Rj over 2. Okay, so this is better. Okay, so this is telescoping sum because the Rj is a difference which is sitting over here. So it will be conserved. And you know, it's sort of the control parameter for the free spacing. So it's like the inverse of the density. So if I change p, then you know, I can control how dense the particles are. So p is pressure-like. And I say pressure-like because you know it's a usual problem with sort of statistical mechanics. I mean, maybe one should beta p because you know this has more physical significance. Anyway, I mean, so it's pressure-like. I mean, it's a control parameter for the density, and it's invariant. Okay. So now I have put here. So this is what I would call the a priori measure. So it's a product. It still has a simple structure. It's a product. And it has this one control parameter which sort of controls the density, and it is invariant under the time evolution. Okay? So it's like the Lebesgue measure for the usual sort of particle systems in statistical mechanics. So but now I must do the Gibbs weight, and then so the Gibbs weight which I put is e to the trace. So I take some function v of L. This v I call confining potential, and you know, I can do a more or less general thing, but you know, just think of something like this. So in order for the partition function to be convergent, I mean, you know, it has to sort of diverge at infinity, and then you know, we don't know exactly what class of v's we can allow, but anyway, I mean, it's sort of a conceptual thing that you know, you should think of a general v here. I mean, v of that type. Okay? So for the p, I mean, I have to be a little bit careful because you know, when I take here a negative power, I mean, then this wouldn't work. I mean, so the pressure is always positive. Okay, and then we have a V. So you see, now we have sort of, as thermodynamic parameter, we have a number and we have a function, right? And we have sort of already, you know, this is a function. So we have already infinitely many parameters in our Gibbs measure. Okay, so now let's look, you know, for a second, you know, what is behind this definition? And so behind this definition is that, well, there's sort of two things. I mean, first of all, I mean, you can define, sort of introduce let's see, yeah, you can sort of define sort of like a more discrete labeling rather than having this function. And this I would take as trace L to the power n. Okay. Now this I can write in terms of the sum of all the eigenvalues to the power n. And since the eigenvalues are conserved, also the Qn will be conserved. Okay. But I can also write it, I write the trace, so I write this j equal 1 up to n. And then, you know, I have Ln, and the matrix element Jj. I mean, this is, you know, the density, which I like to denote by Qn of j. And so you see that it sort of satisfies what we want to have. I mean, you know, it's something which is conserved, but it has a density which is local. I mean, this is a tridiagonal matrix, and if I take the nth power, you know, it will be maybe sort of not tri, but n whatever, you know, it will have sort of anyway. I mean, there will be, you know, there will be a band of size n where I have some matrix element and outside it's zero. So this object is local. So we have a local density, and I didn't emphasize the introduction, but you know, hydrodynamics sort of is made under the assumption that you know the charges or you know the fields which we are looking at are sufficiently local. You know, it's a separate story when I look at the sort of long-range interactions and all kind of things. So I'm sitting here on models which have local densities. Okay, and so let's have a look. Okay, so now why did I put the trace to the? Well, I mean, you know, okay, so VL to the power n. What did I do? Yeah, you know, maybe I can just take the trace. So of course, you know, if it's a smooth function, I mean, I can expand this in a power series. I can put sort of generalized chemical potentials here, and then I have the trace to the power n, right? I mean, this is just expanding this function. And okay, so in the literature you will always find this sum. I never. I mean, of course it's okay, but somehow conceptually I never liked so much the you know. It looks like we need sort of like an analytic function or so, but this is besides the point. I mean, the main point is maybe it should be continuous and should increase to infinity. Okay, and so I like this notation, which sort of, you know, is simply, if you want to, you can always think of this function in terms of a power series. In fact, you know, the examples which I show you are exactly what this is. I mean, I can compute what is the trace of L. I mean, that's just the sum of the diagonal elements. So I get 1 up to n, Pj. So this will be obviously the total momentum, which is of course conserved. And I can also compute the square of this matrix. So this is the sum of all, you know, I have to square each matrix element. So I get the summation over j of Pj squared. I mean, so now I have summed all these elements over here. And then, you know, I get twice Hj squared. Hj squared twice. And this, you know, when I have not written down the Hamiltonian for you, but you know, this you discover as it's twice the kinetic energy, so this will be the energy. And so you see that if I want to do something which is thermal, then what I have to do is I have to well, then you know, this confining potential is simply the V of W is of course simply 1/2 beta times W squared, right? And this is sort of still a nice case because when you look at this expression, I mean, you see that I still get independent matrix elements. So let's think for a few moments about thermal equilibrium. So of course I can go on with these powers, but you know, there are no names anymore. I mean, it's just sort of the nth power of a matrix. And let's see. So maybe I look for a moment for thermal. Okay, and so now you have to look at this expression and a sixth expression, and you see that this is still a sum. And so, you know, when I put this up in the exponential, I get still a sum. So I still have independence. Okay. Now, what is the distribution? Well, so you know, so the diagonal. I mean, this is just Gaussian. It's just a Maxwellian, right? I mean, so this is Gaussian. I mean, because you see, I mean, I have the dpj, and I have from this formula, I have the pj squared. I produce the minus. Okay, so well, beta. I have the beta I put here. Okay, so it's still Gaussian, and it terms temporal, and so then I have the after. I just say, well, I mean, okay, so maybe I should write the pj's are Gaussian distributed, and the hj. Well, if you look at their distribution, I mean, you know, it's also quadratic, but then I get this prefactor, right? I mean, so you get something like whatever, you know, in distribution e to the minus x squared, and then a prefactor which goes like x to the p minus 1 because I have this one. Okay. And the HA is, this is what in probability is called chi-distributed. You know, it's just tabulated. Well, you can do, okay, anyway, so it's a standard distribution, okay? So what I want to emphasize is that in the case of Toda, when we look at the GGE thermal equilibrium, the matrix elements are still independent. And now you might think you can easily do computations. I mean, that's not the case, but at least it's a simplification. If I go to a general potential, or maybe I add a quartic term over here, or do whatever, I mean, some more complicated potential, then of course I get correlations. And then the matrix elements are no longer sort of, you know, it's a slightly more complicated and less studied situation. Okay. So this is one thing. And then the other thing, which somehow, you know, I somehow said, but I want to emphasize is that L is random matrix, a very specific random matrix under GG. You see, I give me, you know, I give myself the pressure and then this confining potential. Then I have here, you know, the correct distribution. And under this measure, I mean, L becomes a random matrix. Okay, so it's just sort of, you know, focus your mind that you know, now the Lex matrix, which before, you know, we have maybe thought about sort of like a deterministic matrix, is actually a random matrix, right? And that, of course, you know, you see that there's a lot of studies on random matrix theory, and which maybe do not look exactly at this case, but you know, I mean, there are many tools which you can use in order to make progress. Yes.
If I'm doing statistical mechanics, I would have dpj, dqj, and you did a change of variables.
Yeah,
there.
this is dp dq.
Yeah. Where did the variable p come from? The pressure. I don't understand where it comes from. Did we add it?
Where the p comes from?
Yeah. Did we add it by
Well,
hand,
it's, you know, it's just a grand canonical. Well, no, it's a canonical ensemble where you have sort of, you know, random positions and you want to control the density. It's nothing else than that.
I see.
Okay, so this would be, I mean, you know, if you think in the dpq, I mean, you would, at some point, I mean, you would say, you know, what is the density of particles, right?
Okay.
And here you do it in this particular way, right? But you know, this would then saying that I'm doing the canonical ensemble, but with a random distribution of points, right?
Okay. And did we remove like the zero mode? Because when we do the change of variable, there is only differences. So
what was that?
Like,
what is zero?
Like RJ is the difference of two coordinates. So there'll be like one translation variable.
The HA sort of is always the distance between, between qj plus 1 and qj.
Yes, but I can always push them by a fixed coordinate and that by a, and that wouldn't appear in the integral. So is that removed?
That's correct. Yeah.
Okay.
Okay, so let's see. Okay, so now let's see. Okay, so now what do we want to do? Yeah, I'm still doing stacked mechanisms, so we want to compute maybe the free energy. Okay, and so the way how to do this is, you just follow the rules. I mean, you put your box, right? I mean, here, size L, and then you have n going to infinity, and you have L going to infinity. And well, I mean, you want to have a free volume which goes to a given value, which is maybe nu, right? I mean, so this is what you want to do. And then, you take the log of the partition function. It's just what you learn, okay? Now, usually, I mean, you just take a box, but the box is sort of, I mean, you could do a box. I mean, it should work. But if you want to do a computation, with a box, even for the thermal case, I mean, I have no idea how to do that. And so you have to make a very careful chosen box, which looks like this. And so for this discussion, I have to assume that the nu is, I mean, the free volume is positive. I mean, you can compress the particles very much, and then the free volume is actually negative. But these are two cases which one has to discuss separately, and I'm assuming here that it's positive. And so the potential which I'm putting here is now, so this is now the box potential. Okay, the box potential is taken as e to the plus q1. I mean, so for the last particle, I have sort of this decay here, and it only acts on, well, I mean, you see, if I take a positive, if I make this positive, then the particles are sort of almost ordered. I mean, once in a while there could be an error, but mostly they are ordered. And so you can think that, if I confine the first particle to here, then the other one sort of, confined also. And then you have to do the other one on the other side. And this is plus e to the minus un. Okay, and then you have to make the Swanks correct. And if you do the computation, you have to put this with e to the minus L. So this is a very, very confining potential. But for this potential, you can do computations. I mean, otherwise, I wouldn't know what to do. But there's sort of a general sort of theorem, if you want, so that I mean, well, I don't know whether one can really apply it to this case, but I mean, this the way I do the free energy should be sort of independent of how I put the boundary conditions. Okay, so now I do this, and of course, I'm not going to continue any further at this stage, but I want to point out one very important observation. So you look at this, and then there's some not so obvious algebra, which of course I'm not going to explain. But the main thing which I want to point out is that we actually obtain what in statistical mechanics is called a mean field model. And this goes back, I mean, not with this language, but this goes back to Young and Young in their famous paper about the delta Bose gas. I guess Young was 1968 also, something like that. Anyway, so I put here, no, this is the wrong place. Maybe just a moment. Well, okay, never mind. It's also says in sort of, I guess 1969, maybe, okay. And so I want to explain you this mean field Kerr vector, right? So let's do a very simple case. I mean, so let's just do the 1D Ising model. Okay? And so what is your Hamiltonian? I mean, well, so your Hamiltonian is that it's in one dimension. I mean, so I sum over I minus j nearest neighbors, and then I put here sigma I, sigma j, right? I mean, this is your Hamiltonian. Okay? Now this is a local interaction. This is not a mean field interaction, right? Of course, you can figure out what the free energy is, but that's not the point here. I want to say that you can now change the model into a mean field model. So you make the mean field model. Well, I mean, you just do 1 over n, and you do sum over all sides, right? 1 up to n, and then you do the same sigma I, sigma j. And why is this sort of anything useful? Well, because so first of all, you see it's still extensive. I mean, because I have n squared terms and I divide by 1 over n, so it's still extensive. But you can rewrite it in the following way. I mean, so it's n, and then you take the summation j equal 1 up to n, 1 over n times sigma j, and you simply square this, right? And so this is sort of the, I mean, I have the 1 over n here in front of it. So this will be the macroscopic mechanisation. And so you see, it proceeds very different from this case. I mean, once I can sort of represent this, in terms of the magnetization, then you write down sort of the free energy and you check a little bit. I mean, it's clear that I will get a variational problem. I will get a free energy functional, and then I have to vary this free energy functional to get the correct thermodynamic free energy. Because you see, I have sort of expressed, this statistical mechanics problem already in terms of a field which has a macroscopic, which is self-averaging. Okay? Now, it's a little bit surprising, but when you know about the delta Bose gas, maybe not so much, or when you read the Yang paper, that in our case, the same mechanism appears. Of course, the model itself is much more complicated, but the point is that at the end of the day, you will get a free energy functional. And if you vary this free energy functional, you get the free energy and other things which I'm going to tell you. And so I will sort of make a huge step and tell you what is the free energy functional in the case which I'm looking over here, right? Okay, so now comes the free energy. Okay, and so this is a functional of some rho. I mean, rho is some density which will come sort of later, and then the integral over dw of rho is equal to 1, so it's normalized. And the way, so I get two terms. So I get the dw. So first of all, I get this confining potential minus mu. Okay, so maybe I should give some sort of hint. I mean, the rho w, you should think sort of like the distribution of eigenvalues. I will explain this a little bit more detail, but I just want to get this formula here on the blackboard. I mean, so this term is sort of somehow the obvious one. I mean, here you have now, instead of the pressure, you have a chemical potential. And when you look at this formula, I mean, then you see that it's basically this formula. You see, if I know what the density of states is, I mean, then you would expect that, in the large n limit, I mean, I just have to integrate the confining potential over the distribution of, I just have to know, with what probability did these lambdas are actually appearing, right? I mean, so I will explain this in more detail, but I just sort of want to give you an idea that this term is sort of almost expected from the formula which I wrote you down. But then there's sort of an entropy term, which is the integral over W. And then I write it in terms of rho, log rho minus log rho of S. So this is what the specialists call the space density. But here, just look at this formula. So you can think this of the relative entropy of rho relative to rho S. Okay. And now I have to tell you what is the rho S. Well, so the rho S is sort of it's defined by 1 plus T rho. So you see, I could insert this expression already in this formula, but then it sort of looks not so nice anymore. I mean, you can sort of think of this sort of as a variation with this particular constraint. And T is the dressing operator. which has a kernel which is given by twice the log, let's say, of W minus W prime. So if I take some function and act on W, and now I want to know what this is, then I have to do integral over to W prime. So I have to do the 2 of log W minus W prime. So this is the integral kernel of this operator. Okay, and now here I have this operator acting on the density. Okay. Now the assertion is this is sort of the correct free energy functional for the total lattice. In fact, it's also functional, which governs all the large deviations of the total lattice. If I ask myself, according to these measures, sort of, what is an unlikely distribution, what is an unlikely density of eigenvalues, then, I would have to go back to this particular formula here. But if I sort of do the minimizer, then I get the free energy. Okay, so now we have to do the minimizer. And from this, you get the free energy. So now I have to look at my time here. What am I doing here? Oh, no, I still have 1 hour, 55 minutes. I mean, so let's see. But so how long did I talk now? I mean, this is now not 10. Okay. Okay. Well, you do some computation. Okay. So, okay. So let's see. So, okay. So where are we? Okay, so now okay, so yeah, maybe I should erase a little bit. I have sort of, I mean, I have a somewhat natural break in 5 minutes. I mean, is that okay? Or I don't exactly. I'm not sure how I'm doing this time. I mean, so
you still have 45 minutes.
I still have 45 minutes. Okay, so okay, so let me do 5 minutes, and or maybe if you want to, maybe we do now a little break, because if I just go on, I mean, so people maybe fall asleep. Okay, so let's do now a break, and then I continue. Yeah.
Just take a 5 minute break.
I can erase the blackboard in the meantime. So of course I can ask, answer questions. I mean, so.
When you define the free energy functional, at some point you define some post-free, because you're saying this is.
No, well, no, yeah, okay. So you can phrase it like this, but I don't do it. It comes out of the computation. You see, that's the whole point.
Because it's a mean field.
Because it's a mean, the mean field is not imposed by me, like for the Ising model, but the mean field is really coming from the integrability of the model. You see, it's part of the model that when you do the thermodynamics of such an integrable system, it turns out to be mean field. I mean, it's not obvious from the formulas at all. You see, when you look at this expression, it looks as local as you would think. It has no mean field character, right? But what I'm saying is that when you I haven't told you what the computation is, but if you sort of work a little bit harder on this problem, and when you look, you see, I'm looking here only at the distribution of the eigenvalues. You see, you could also ask about what about positions.
Right.
This I have not touched at all, right? So okay, so I concentrate on the eigenvalues, and then it turns out that when you look at the distribution of eigenvalues, it is of mean field type. Right? I mean, so it's not imposed. I mean, it comes out of.
But where does this assertion come that it would be like a mean field type?
No, okay. So when you look at the beta ansatz, so this is the origin of this. When you look at the beta ansatz, I mean, you have already the 1/n sitting there. Of course, people never thought about this as mean field. It's just sort of, but you do the beta ansatz, and it just comes out that way. Okay. But then when you look, they never use the word mean field. But when you look at the computation which they do, it's clear that they sort of understood that there's some sort of I mean, eventually they write down this kind of free energy functional, right? I mean, sort of. I mean, there's some intermediate step, but in the delta Bose gas, you see this kind of you know, in the young, I mean, you see this mean field structure appearing quite quickly, and they write down sort of a similar type of variational problem as what I did over here. Okay? But yeah, I mean, we are, so to speak, lucky, right? In the sense that you know, you might think that this the thermodynamics of integrable system is something sort of inaccessible. But it turns out that you know, the integrable structure gives you sort of at least some bonus in the sense that you can write down what is the correct free energy function.
I have one more question. So when you have normal like Gibbs ensemble,
yes,
you also have this idea of subsystem.
Yeah.
Would the similar thing also apply for GT? Can I think of?
Well, I mean, no. I think you should really compare this with what you say about the mean field Ising model. I mean, you know, if you can say it about so mean field Ising model is an example where you don't have a field. I mean, you just have a single variable, right? I mean, but you should sort of think something similar for many variables, so to speak, right? And so whatever you think, you know, whatever you sort of feel is natural for the one component Ising model would be natural for the others. So you know, we have not discussed any spatial structure. You see, the spatial structure is totally absent. We focus sort of on one aspect of the problem only. Okay. Very good. So I do here this erasing. Maybe as I erase, maybe there are more questions. I mean, we can sort of answer them. I mean, the DOS, the density of states, and TBA equations. I mean, you know, this is just sort of some sort of terminology from quantum mechanical system, but anyway, I mean, so this stands for density of states, and this stands for thermodynamic beta ansatz, which the density of states is a good name. This one, of course, it's not a good name, but you know, we just use it. I mean, it's fine. Okay, so the question is, you know, I mean, the free energy. I mean, I'm certainly not really interested in the free energy. You know, I mean, who's going to measure the free energy of such a system? I mean, but the real observable is actually what is called the density of states, right? I mean, so this is what I want to do. And now, first of all, I have so now I'm talking about observables which I want to compute, right? Okay, so the DOS is sort of you know, a standard object in random matrix theory. So here I have my eigenvalue equation, and L is my Lax matrix, which is random, right? I mean, so of course these are non-random, but these objects are random. Okay, and then you say that well. Okay, no, this is not correct what I'm saying. So no, okay. I mean, the lambdas are conserved, but of course they are random. You know, if I take another configuration, I will get different eigenvalues. Okay, so I'm focusing on the eigenvalues. This is what is called the density of states, and of course they are random. Okay, okay. So now let's define this. DOS. I mean, I put here an n. I mean, so at the moment I'm still sort of looking at a finite number. I mean, I take 1 over n summation j equal 1 up to n, and then I just add sort of, you know, a delta wherever I have an eigenvalue. Okay. So this is the conventional sort of definition of density of states, right? I mean, so it's normalized to 1, and then each spike has sort of weight 1 over n. Now, in our context, when I take the thermodynamic limits, so which I put sort of merely like n going to infinity, but you know, the way how it's understand in the usual way, I mean, then this will actually go to, so there will be a law of large numbers, I mean, self-averaging. So there will be a limiting rho q of w, and this is sort of non-random. So this is about the general fact, but now we want to sort of, okay, so this object will be actually eventually a hydrodynamic field. So you see, for our hydrodynamic fields, I'm coming back to this, but I may have to make this remark. I mean, so for the hydrodynamics, you know, the fields are what? I mean, I have a rho, I have a density of state W, but now, you know, in hydrodynamics, I mean, this becomes local in space and time. So there will be a function which depends on x and t. And I have still, you know, the dual of the pressure, which was this free volume, which I've denoted by nu, but the nu is not a function of W, it's just a number, but it, of course, will also depend on space of time. So the hydrodynamic equations will be written in terms of these things, right? And very often, I mean, one takes the products and calls sort of these objects and the particle density, which is of W of x and t. It's just a convention. All right, but now let's look at this density. I mean, so the usual terminology is to call this object here empirical. Empirical means that you know, you just look at one given realization of your matrix, and then you compute the eigenvalues, and this is sort of then the empirical density of states. It's the density of states of that one particular sort of sample of eigenvalues. And then, you know, I have many, and then this is sort of like a law of large numbers. I mean, so this converges in probability to some deterministic value. Okay, and now the point is that the minimizer of the free energy is rho, this one. I mean, okay, so sorry, where did I put it? It's the rho q. Here I should have put the rho q. It's the rho q. So what I'm saying is that, you know, you have this functional, and if I minimize, then actually I do get sort of, you know, the macroscopic, I mean, the non-random limit of the density of states. So this again sort of a general fact, but you know, now you know, I mean, this is nice, but we would like to know what is it. I mean, you know, it's a way to compute it, and of course it's obvious. I mean, you know, if you want to do the minimizer, I mean, you have to sort of you know, you have to, it's a variation problem, so you have to determine the minimum, and you use the Euler-Lagrange equation. In fact, it's in our case, it's a unique minimizer. It's Euler-Lagrange, and then you know, this is sort of then written in a somewhat less intuitive form. And well, if I would write down the Euler-Lagrange directly, you know, maybe it would become lengthy anyway. So I'm just telling you when I sort of do this linearization, I mean, what are the Euler-Lagrange equations? Okay, and the way how this goes is that you introduce something which is called the number density. So these are really, you know, I mean, just consider this as definitions at the moment. So I can introduce the density rho n, which is e to the minus epsilon. Everything depends on W. That's the spectral parameter. So this is called the quasi energy because it looks like a thermal thing. Okay. And then the Euler-Lagrange equation is actually written for the epsilon. I mean, so now the claim is that the epsilon is given by the confining potential minus mu. And then we have the dressing, and this is minus, the dressing operator is the one which I introduced over here. This is the operator which has a kernel with the logarithm. And in fact, I mean, I wanted to point out, I mean, you know, this is log. I have to put here a red color here. This is log number 1. I mean, so you know, you will see that there are other logs appearing. But they come for very different reasons. I mean, but this is the first time the log appears here. Okay, and so let's see. So we have this one. Yeah. Okay. So now I'm writing down here I'm writing down the Euler-Lagrange equation, and so here you have the e to the minus. So here you have the e to the minus epsilon. Okay. Okay. And so now you see that you have an equation for epsilon. So you have to solve this nonlinear integral equation. Now once I have the epsilon, you have the rho n. Okay. So now I have the rho n. And now the rho n is not yet the density of states. I mean, but what I have to do is that you know, if I take mu times rho q, which was the rho p over here, but let me still use this notation. It's nothing else but the d mu. Okay, so now I'm done. You see, so this is the way how one has to do the computation. Okay, so this is the end of the story here. Now I will come to the next chapter, which is 5. I mean, so you see, now I have sort of, I have sort of done the thermodynamics of the system, okay? And so yeah, okay. And but now the next point is I want to do the currents, right? Okay, so let's think for a little bit. I mean, so now I have the charges. I mean, so I mean, remember that there's still this underlying particle system, and so I use the definition like usual sort of for fluids or so. I mean, this will be now a continuum field, and the way I define it is that I do the sum j equal 1 up to n. Let's say I put the delta of x minus qj. So qj are the underlying q's, I mean, which we have forgotten a little bit, but of course they are still there. I mean, in the evolution equation, of course, I have to know what the initial q's are. And well, then you just multiply this with the density of your charge. So this is L to the n, and here I take the jj's. And then you look at the time derivative of this quantity. Well, it satisfies, of course, the conservation law. So this is sort of like the conservation law, which I put at the very beginning of the talk, right? And now I'm not spelling this out. I mean, of course, well, I mean, this is okay. Well, xt. I mean, okay. So this is also xt, and then there's the index n, and this is equal to 0, right? Okay, so this is not the microscopic current. I mean, I can write down the formula. It's not so complicated, but it's not very important. I mean, it's just the point is that this is sort of the traditional definition, and then you indeed have the conservation law.
But I have a question. I didn't understand. So F was coming from the stationary state, the GG. How did the time enter? Why is the time evolution now given?
No, where are you looking at?
So you read the statement.
No, there's no time. I'm just saying that what I'm really interested in is not the F. I'm interested in the minimizer physically. And then now I'm just writing down the Euler-Lagrange equations for that minimizer. That's it. There's no time here. That's completely static, right?
Okay.
I just wanted to indicate that it's not only abstract, but there's a concrete computational way how to do it. I mean, you take this equation. I mean, you solve. I mean,
because you wrote the hydrodynamics with the weak convergence with this time dependence. You write this equation with the nu, which is the weak convergence.
No, mu is just a number. To me, mu is a chemical potential. Okay. No, I just want to demonstrate that there's a concrete computational thing which you have to do, right? I mean, so I mean, except for a few cases, I mean, you cannot sort of get an exact solution, right? I mean, that's too much to ask. For thermal states, I mean, you can actually find the minimizer and you can actually, give really the solution. But that's sort of exceptional. Okay, so let's see what we have to do here. Let's see. Okay. So now what we want to do is we want to, you see, this is sort of the hydrodynamic sort of procedure. I mean, what we want to know is actually in the steady state, what is the average current? Now, these things are translation invariant. So the thing which you really would have to compute is, the nth current at the origin. At the origin, because it's translation invariant in X, but it's also translation invariant in T. So if I use this somewhat complicated notation, I mean, this is the average which I would have to do, and then I have to take the Gibbs state with this pressure and with this confining potential. Okay, so this looks like a complicated problem. And the reason why it's a complicated problem is that when you look at this current, this is, of course, it's not a conserved quantity. So it will also depend on the eigenvectors. But the eigenvectors I do not control, and doing average over eigenvectors, I have no idea what to do. Okay, so now I am stuck. You see, this one was, the mean field was sort of, once you had sort of these tools, I mean, it was okay, but this one is a really difficult question. Okay, now there's this sort of one sort of funny identity which I sort of discovered some time ago, is that so I take the average. So I omit now this index here because otherwise it's sort of too long, right? I mean, so I look at this quantity here, this average, and I differentiate it with respect to the pressure. And then what I find is the following expression. It's the integral over dx. It's again, I mean, you know, average with respect to P and V. And I have to subtract averages. I mean, so it's truncated. And here I have the Qn of x. And then I have here the Q1 at 0. So you see, this is telling you that this derivative is related to, you know, sort of the fluctuations or to the correlator of the conserved charges. This is an equilibrium quantity, which I, in principle, you know, its mean field, I can somehow work out. And this is a very general identity. I mean, it doesn't work for all models. I mean, Takato, you know, has explained me how to extend this identity to quantum systems. And so this is something, you know, which is always true. But now, of course, I have to work out this, which I'm not going to tell you, but I'm just going to tell you that what the answer is. So now I want to write this average. You know, so these are the nth moments. Well, I wanted to erase this. Okay, so now I have here the P, the V, and truncated. So I can write this. I mean, just like I had for the charges, it's an integral over W. And this n kind of comes in as a W to the power n, right? I mean, so this is not so difficult. And then I get something which I sort of write as a new rho Q of W. So this is the density of states which I'm looking at, and then this is the mu. And sort of provisionally, I call this here V effective of W. Okay, I mean, this looks now completely arbitrary, you know, but now if I do this, and if I manipulate, you know, all the expressions, then what you end up with is a very familiar formula, namely that the V effective, I put here V, I mean, because that's the conventional thing, is that it's V. I mean, this is sort of like the bare velocity. But then, you know, because of collisions, this is the bare velocity of a quasi-particle. And because of collisions, you know, you get some correction. And this correction is written as W. So I have to give you, you know, the state which I'm looking at. So this is the new rho Q of W. And then there is the logarithm here. It's logarithm number 2. I'll tell you in a second how this logarithm is computed, and then V effective W minus V effective of V. So V effective, you know, you have to solve this linear integral equation, and then the V effective will be some function of the rho Q. Okay? So this is a famous equation, and let me sort of tell you the way how you sort of, you know, read it in any kind of review article on generalized hydrodynamics. So here's sort of, you know, the picture which they always give, which is certainly a correct picture. And so, you know, here I think sort of like X, and this is time. And now I want to look at the quasi-particles. So these are these objects which sort of essentially, you know, maintain their velocity. Okay, so now I look at maybe a quasi-particle, you know, which is sort of like a bare velocity V. I mean, it would just go along a straight line if there would be no interaction. But then, of course, you know, there's a medium. I mean, there are other quasi-particles here. There are other quasi-particles here. And then, of course, there will be collisions. And because of the collisions, you know, the actual trajectory which this quasi-particles is doing is sort of, well, maybe it jumps, or, you know, maybe other more complicated whatever, you know, there's something like this. And eventually, you know, it will go with a velocity, which is V effective. And it's this velocity which is computed through this integral equation. Now, this, of course, is the basis of you know, generalized hydrodynamics, which by the inventor, the sort of, you know, back in the sort of almost 10 years back, I mean, you know, they had already this formula, right? I mean, this is not a new formula at all. And in fact, I mean, you know, it's very sort of confirming that through this mechanism, you get exactly this formula. You see, this picture works very well if you are at a very low density and if sort of, you know, the collisions are actually sort of just pair collisions, and then of course it sort of works okay. But you know, you might wonder whether it's actually also true at high density. But when you look at this derivation, there's at no point in these identities there's any restriction on the density. So, you know, this is sort of what everybody believes and has checked, and in many cases, I mean, that this is sort of a correct formula. Okay, so now how does the logarithm appear? Well, the logarithm appears in a very trivial way, because you see what you are saying is that, you know, when I have now here this collision, you know, I can do as if they are really just two total particles colliding. So I just do the very simple computation of that R double dot. So this is, I take two total particles, R is the spacing between them, is given by 2 times e to the minus r. And now I'm computing, you know, when I solve these equations, I mean, so you know, maybe it looks like this. I mean, so, you know, maybe, so maybe I have to do a drawing here, so otherwise I understand. I mean, so maybe I have one particle which is coming in here fast, it's sort of going out slow. And then of course, you know, I must have the other particle going in and then going out slow. But, you know, then there will be a shift, you know, it will jump from this value to this value, right? The quasar particle, okay, let me indicate the quasar particle here. So one quasar particle is this one, and this one is sort of the other one, this one quasar particle, and then if I follow, you know, they have the same velocity, maybe not in my drawing, but anyway, so, okay. But then there's a shift, you see, I mean, you collide and then you jump, or, you know, you place on a certain amount, and if you just have two particles, you solve this differential equation and you find the logarithm. Okay. So now we have log 2, and you see, this a little bit surprises that you know, where am I? I had the red one. I mean, so it's a little bit surprising that you get the log. Of course, I mean, you know, if everything correct, I mean, you must get the log. But the point is that here the log appears by a totally different mechanism. Okay, so this is the log 2. Okay. Now I can write down the hydrodynamic equation, which is now the obvious one, and you write ddt of the rho p. I mean, this is now, you know, I included, let's see, yeah, I put here the definition somewhere. Yeah, here, I mean, it's just the product of these two things. And then there's this dx, and now the current is, you know, the way how I wrote it in this ansatz. Let's see. Ah, okay, yeah, right up here, right? Okay, so you get the dx, I mean, you get the rho p. You multiply this with the effective velocity, which is now a function of rho p, and this equals 0. And all these objects are functions of w, the spectral parameter, and of x and t. So this is the GHD. Now, the beauty of this formula is that, first of all, it's very intuitive. And because it's so intuitive, you can very easily sort of extend this to other cases. Right? And you know, the first thing what you do typically, if you have a system which you haven't yet quite understood, you want to write down this equation, you just sort of copy this philosophy here and try to figure out, you know, what kind of kernel you have to put here. Okay, so now maybe we can have the slides. I mean, I don't know, I still have a few minutes. I mean, so. Okay, so one thing which we did and which works extremely well is sort of, we look at sort of the space-time correlator in thermal equilibrium, but I don't want to enter into this. I want to explain you a very new development, which I find very exciting, and so I really would like to sort of give you a rough understanding of this. You see, in this picture, I mean, well, here's now covered. I mean, I talked about the quasi-particle. You listen to any one of the lectures sort of doing this thing. I mean, you know, here's the quasi-particle. You really don't know what the quasi-particle is. Of course, you know, you use many words to say what it is roughly, but, you know, to give really a definition, I mean, you know, it's very hard. And so here, I think in the next slide, so here, I think in the next slide, you know, I put this picture from my book. I mean, so here is the dynamic. So T goes this way. I mean, so these are just 16 total particles, and you do, you know, just simulation of this one configuration. Now, you know, the description of the quasi-particle is you follow sort of essentially its velocity. Okay, so I did this by hand. I mean, you see that you know, I mean, once in a while, I'm not. So you can see the initial velocity. I mean, right to the left. Now, once in a while, I mean, you see maybe, you know. Maybe if I'm over here, you know, this is in periodic boundary conditions. I mean, so, you know, over here, maybe that is really the quasi-particle. But is it really the quasi-particle? And then you see, I mean, if I have sort of many successive collisions, I mean, where is the quasi-particle, okay? So as I said, you know, when you take a very dilute system, of course, you know more or less, right? But if I take a dense system, you know, you have a little bit of course, somewhere it must be the quasi-particle, but you know, what exactly it is. Okay, so now comes sort of this nice observation that we really have a nice definition of the quasi-particle, and it goes, you know, in a very simple way. I mean, so the main point is that the quasi-particles are actually the locations. I mean, the locations of the eigenvectors. You see, we talked a lot about the eigenvalues, and the literature is full of eigenvalues. Nobody ever asked the question, well, except for very few people, nobody ever asked, you know, what is the significance of the eigenvectors? Okay, and so here I give you a very simple example, you know, which you know, over here, I mean, so I just imagine that, you know, here I'm strongly interacting, and I observe, you know, the very first particle which is coming in with lambda 1, and then it's sort of, you know, it's complicated. What I told you, this is a scattering situation, and it comes out, of course, you know, with the same velocity. I mean, this is sort of the scattering thing. Now, when you look at the corresponding eigenvector, I mean, of course, it's easy to figure out. I mean, you see the eigenvector starts here as 1, 0, 0, because, you know, I'm looking at this first one. But then it sort of does some complicated motion, but then it eventually comes out on the other side. So it does exactly what you know, what the quasi-particle should do. You see, the quasi-particle has sort of it knows its eigenvalue, right? But then, you know, the eigenfunction tells it knows its eigenvalues. I mean, this is sort of linked to it, and it can never lose it. But then the eigenvector tells you sort of where it is sitting in physical space. Okay. All right, and so now you can, I mean, you can look at the dynamics of these eigenvalues. So you know, it's a pair. I mean, so this is one equation which governs the motion of the eigenvalue. You start with a specific eigenvalue, and you solve this equation. This is space-time dependent. So you know, it's a little bit complicated. We would never do it. And there are sort of, you know, I mean, so you know, I'm Bulshardani and company mentioned they have 3 lines on this and 2 pictures, but you know, it's very brief, and there's also sort of a more recent thing by Lepri. I mean, Stefano Lepri. So he also observed this, but he wanted to use this sort of as studying perturbations of the integrability, and the very beautiful. I mean, it's sort of more mathematical work, but a very beautiful work is the one of Amalaga, and I'm sort of relying on this. Okay, and so here sort of, you know, the very obvious definition what you do. I mean, so now this is the position of the quasi-particle, and what I'm doing is, you know, I'm looking at this eigenvector, and now the main point is that you have in this system Anderson localization. So your eigenvectors are sort of, you know, sitting on few sides. I mean, the wave, the envelope of your eigenvector is sort of exponentially decaying. And so now you see the obvious definition. I mean, so here is, you see these eigenvectors are in label space, but now I want to go to physical space. So I'm simply saying that the quasi-particle is sitting on the chase total particle with this particular weight, which is just a square. You know, if you do quantum mechanics, it looks quite familiar. It's just a square of the eigenvector. Okay. Okay, and so now let's have a look. I mean, so this is now from Alberto. So now you see 200 particles. Now you see, now I tell you, where's the quasi-particle? I mean, you will not so easily see this, right? But now I use the definition, and now everything sort of comes in place. So here, wait a second. Yeah, okay. So maybe I let's see. Maybe yeah. Okay. Okay. Maybe I don't have so much time to go. Well, yeah. Okay. Let me see. No, let me first simply show this, right? I mean, so here you can see that what I mean, the red line is now our definition of the quasi-particle, right? I mean, so it's a little bit broadened because, the eigenvector is sort of well localized, but not so well localized, maybe 5 sides. I mean, so you have some intrinsic thickness. And you can see that you can sort of compute the violet line. I mean, that's just the eigenvalue. So this is the bare velocity. Okay, and now you see, all these collisions, and you see that the bare velocity is changed to the effective velocity, and this is sort of the blue line. And one thing which I find very instructive is you can, of course, I mean, you just differentiate in time. You get the velocity of the quasi-particle, and in this definition, the velocity is defined at every time point. And so this is what is plotted over here. I mean, so here in this picture, I mean, you see it's the velocity, and you see that it's sort of fluctuating. Of course, I mean, once in a while, maybe, it's not so well localized. So, anyway, I mean, it's a fluctuating quantity, and even for this one single configuration, I mean, when you do a sort of average over this one sample, I mean, you get already a value which is very close to the predicted value. And this is the bare velocity, and here you see. Okay, and maybe I have another. Okay, here's another example just to see that, it looks the same. Okay, so the big invention is that we now have sort of like a well-defined definition. But what Amol, I have to go back. I mean, what Amol actually, no, sorry, yes, that's the other way. Okay, so, okay, here I am. Okay, so you see what Amol actually tells you is that there's sort of an implicit definition of this eigenvalue position of a quasi-particle position, which is verified with a very high probability. And you see, it's quite intuitive. I mean, first you have here the bare velocity, so that's the initial point, and this is true at any time. I mean, so here is the position at time t. This is the time t equals 0. This is just a free motion, and now you simply count, in some sense, what is sort of the logarithm which is picked up in the various collisions, right? I mean, here I look at the position of the particles to the left of the alphas particle, quasi-particle, which I'm looking at, and then I have to sum over those, and I have to sum over those. I mean, these sums are sort of, huge sums, and there's a lot of cancellation, but nevertheless, I mean, this is sort of a correct formula. Okay, so this is, I'm really out of time, I think. I mean, anyway, yeah. Okay, okay, I would like to sort of say a little bit more, but I want to just point out that it's really what people know in condensed matter physics, the one-dimensional Anderson localization. You see the eigenvectors, they look really like this one up here. You see, I mean, there's a center. I mean, there's an envelope which sort of decays exponentially. Gives decays with a particular decay parameter. And it's this envelope which sort of tells you roughly what is the size of the quasi-particle, right? I mean, so it's never, I mean, of course, at infinity, it's sort of a delta, but before it's sort of distributed of sort of neighboring trajectories, and the weight is given by the square of that quantity, okay? Okay, so now in this formula, this is the last thing I want to say. In this formula, I mean, you see also the log. So what does Amol do? I mean, does he where's the log 2? I mean, does he solve for just the scattering? Oh, here, no, here was, okay, it's covered here. Okay, so the log 2 was when you just computed the 2-particle scattering, okay? Now, does Amol ever do 2-particle scattering? No, of course he doesn't. I mean, this sort of, it's a much too localized information. I mean, so So this is not how this logarithm appears. And so how the logarithm appears, it's just one slide which I still want to show, is through a famous result which goes under the name of Thouless relation. So Thouless is, very famous condensed matter physicist, and at that time, this Anderson localization was sort of a hot topic, and he sort of argued that there should be, a very simple relation, and maybe it's too late to go through the slides, but I will just look at the top line. So the Thouless relation is a relation between the Lyapunov exponent, which is explained if you don't know, and the density of states. And you see that the two things are connected through the logarithm. And it's the logarithm of the Thouless relation which appears in the Amol, in the sort of Amol theorem. So we have three ways how the logarithm appears. One, through a totally static computation, which sort of, at first sight has nothing to do with logarithms whatsoever. The second one, which is doing the simple two-particle scattering, which is sort of, in some sense, the easiest one to do at all. And the third one, which comes through the Thouless relation. Okay, so I think I should stop here. Thank you for your attention.
So if I look at time t, and I look at all these quasi-particle positions, will they be related to the positions of the actual particles in some obvious way?
No, I mean, well, I mean, this is label space, right? I mean, so they can be, I mean, okay, the position is sort of a well-defined position, right? It's just this number, right? I mean, but they are typically sort of concentrated on, I mean, if you do the two-particle collision, you can follow, much, first they are concentrated on one, and then they somehow interpolate them. And the way how they interpolate, I mean, this is sort of on a microscopic scale. That will not really change the macroscopic behavior. If you make a slightly different definition of it, I mean, I more likes to look at the maximum of that. It doesn't make a difference. I think the one with the second moment sort of, the square of the eigenvector sort of looks to me sort of for computation sort of, the nicest one. But yeah, no, I mean, well, they can become very close. Yeah, I mean, it's, yeah.
This connection to the eigenvectors, would it also explain the diffusive spread of the tracer particles?
Okay, yeah, that's a good question. Yes, that's a good question. I mean, so here, just tell you what the question is. Okay, so you see, I mean, this rather random fluctuating velocity, and so it's very natural to say that, this quasi-particle, of course, it has a, effective velocity is the mean, so it's sort of like an asymmetric random walk. It has a non-zero mean, but you would think that, it should be simple Gaussian, right? Okay, so we don't know yet. I mean, of course, this is what we expect, but we haven't done any simulation, and so it's something to be studied. In the literature, you can't, based on this kind of TBA formalism, I mean, you can find paper by Benjamin and other authors, a formula for what the diffusion coefficient actually should, the diffusion coefficient of that Brownian motion should be. So that there's a prediction. It's again, you have to do TBA, and there's some formulas, and you have to do some tracing. Anyway, there's a very concrete formula, and of course, yeah, it would be a very interesting question to know whether. This formula, also relies on some assumptions, right? I mean, so it would be interesting to know, whether this, first of all, when you do simulations, whether you reproduce the formula, which I somehow would expect. But there's also another question is I mean, it might depend on your specific parameters, right? You see, I mean, in principle, the diffusion coefficient depends, let's say thermal, then it depends on the temperature, and it depends on the pressure, right? I mean, how does it depend on it? You see, you can have situation where the particles, you can actually tune your system so that the mean spacing or the free volume is zero. So all your particles are sitting essentially on top of each other. I mean, what is now the diffusion of, okay? So no, I mean, these are nice questions, but at the moment they're completely open, yeah. No, but it's a very natural question, yeah.
And what would be this analog in the classical case, like hard rods, when you, this ideas of Anderson localization, would it translate?
Yeah, okay, yeah, I think, okay, for hard rods, I mean, you do sort of directly a solution. I mean, so I don't know whether there's any Lax matrix whatsoever. At least, you know, I don't think people have tried because, you know, there are other means to do the hard rods. But let's say for the Kalotschora, I mean, there's also a Lax matrix. I mean, for the Ablavitz-Ladek, I mean, there's also a Lax matrix. So there are other models with Lax matrices where you can sort of, you know, play exactly the same game. Yeah.
If there are no more questions, let's thank Herbert for a wonderful lecture.